Ratio test. Now we're going to look at our final test. So we have the sum. Oh, this should say ratio. I'll fix that. Okay, so if I have the sum of a sub n and we know that's a series with non-zero terms, then we have three outcomes. One is that if the limit of the next term over the term before is less than 1, then the series converges. The next is if the limit as n goes to infinity of the ratio of the next term over the previous term is greater than 1, then the series diverges. And if it equals 1, it's inconclusive. I think about ratio tests as kind of like the geometric series test. Okay, we're looking at how fast the series is growing term by term. Okay, so let's go ahead and look at a few. We're going to determine the convergence or divergence of the series. So I'm going to take the limit as n goes to infinity of the next term. So it would be 2 to the n plus 1 over n plus 1 factorial divided by the current term, 2 to the n, or a sub n, so 2 to the n over n factorial. Okay, so when we divide, we are just multiplying by the reciprocal. So this is just equal to the limit as n approaches infinity of the absolute value of 2 to the n plus 1 over n plus 1 factorial times the reciprocal of a sub n, so n factorial over 2 to the n. From here on out, I'm just going to set up my ratio by multiplying by the reciprocal so I can take out this step, okay? All right, so what I know is that the limit, I will write this out for you. You could really do this in your head. All of these terms are positive, so I'm going to have 2 to the n. If you're adding exponent, it just means that you're multiplying the bases, so times 2 to the 1 over n plus 1 times n factorial, okay, times n factorial over 2 to the n. So again, this is like 1 times 2 times 3 times 4 times n plus 1. So this n factorial is going right here, and then we have an extra term of n plus 1, okay? So I see that the n factorials will cancel, the 2 to the n's will cancel, and this is going to leave me with the limit as n approaches infinity of 2 over just plain n plus 1, okay? And when I take the limit of that, I get, well, 2 is going to stay constant, and then I'm dividing by infinity, so that's 0, which is less than 1. So the series converges by ratio test. Next. Okay, so I'm checking off, like, let's go ahead and use the ratio test because this looks complicated. Okay, so I'm going to have the limit as n approaches infinity of the absolute value of n plus 1 squared times 2 to the n plus 1, so n plus 2, over 3 to the n plus 1. Okay, and then multiply by the reciprocal, so that would be of a sub n, so 3 to the n, over n squared times 2 to the n plus 1. Okay, so I will again expand this so that we can see what cancels. Okay, I have n plus 1 squared is just stays n plus 1 squared. 2 to the n plus 2 can be written as 2 to the n plus 1 more factor of 2, right? Plus 1, all over 3 to the n times 3 to the 1 times 3 to the n over n squared stays, and then this could be n to the 2 to the n plus 1, since we want to cancel it with this others. Okay. All right, I actually can drop the absolute value signs because I know that all of my terms are positive. So I have 2 to the n plus 1 cancels. 3 to the n cancels. Okay, and I think that's it. So let's see. The limit as n approaches infinity of n plus 1 squared times 2 all over, let's see, n squared times 3. Okay, so this is ETC because right here I have my highest terms are n squareds. So I just what I do is I just divide the coefficients of 2 over 3. So I get the limit is 2 over 3, which is less than 1. So the series converges by ratio test. Excuse me. Okay. All right, a couple more. Okay, so I am going to use ratio test here, even though there is a to the n power, because I said so. Okay, so I'm going to do the limit as n approaches, well, we're going to use ratio test because we don't know how to take the limit of n factorial to the 1 over n. Okay, so that's why. So I have the limit as n approaches infinity of the absolute value. This don't equal. I'm using this to evaluate this series, okay? So I have the next term, n plus 1 to the n plus 1 over n plus 1 factorial times the reciprocal of a sub n, so n factorial over n to the n. Okay. I have the limit as n approaches infinity of, I can write the base of the numerator as n plus 1 to the n times n plus 1 factor of n plus 1, okay, all over, I like to put the n factorial first, and then the extra term of n plus 1, okay, and then times n factorial over n to the n. Okay, so I end up with these n plus 1's cancel, the n factorials cancel, and I get the limit as n approaches infinity of n plus 1 to the n over n to the n, which is the limit as n approaches infinity of, well, I'm going to take out the power of n, so n plus 1 over n, and then I'm going to divide those in. So the limit as n approaches infinity of 1 plus 1 over n to the n, and this is the definition of E. This is E. Okay, so E is greater than 1, so the series diverges by ratio test. Okay, so we're going to do the last one, the sum from n equals 1 to infinity of negative 1 to the n over, or times square root of n over n plus 1. So I'm going to set this up, the limit as n approaches infinity of the absolute value of, so I don't really need to worry about the negative 1 because we're taking the absolute value. Okay, so I can put it negative 1 to the n times the square root of n plus 1 over n plus 2 times the reciprocal of a sub n, which is, well, I'm going to put negative 1 to the n times n plus 1 over the square root of n. Okay, so the absolute value signs is going to make all of the terms positive, so I don't need to worry about the negative. And then I see that nothing cancels. So I'm just going to rewrite it. The limit as n approaches infinity of the square root of n plus 1 over n plus 2 times n plus 1 over root 2. All right, so I think this is going to be easier if I rearrange so that, oops, this is this, whoa, the square root of n. Okay, I think it's going to be easier if I rearrange so that the square roots are together. So n plus 1 over the root n times n plus 1 over n plus 2. And I can see individually that these fractions are of equal power. So the root n is 1, has a leading term of n to the 1/2 power. So I'm going to divide the coefficients, which is 1 and 1. So the limit of the first fraction and the green fraction is 1. The second fraction, they also have equal degrees. So I'm going to divide the coefficients to give me 1. 1 times 1 is 1, which is equal to 1. So the series is inconclusive by a ratio test. So we need to choose something else. And I remember that this is an alternating series. So why don't we just try alternating series test, which also uses nth term test, okay? So we have the limit as n approaches infinity of a sub n, which is root n over n plus 1, okay? So what I know is that the bottom rises faster, the linear function rises faster than the square root function. So this series, or this limit, is going to approach 0. So that's our first condition. Number 2, the next term, n plus 1 over n plus 2, has to be less than or equal to the square root of n plus 1. And I know that you're dividing by a larger number. The value of root n plus 1 is not going to be very much bigger than root n. So this is going to, the next term is going to be smaller than the term previous. Basically, the series terms are decreasing, okay? So here we met both conditions for the alternating series test. So the series converges by alternating series test. Done.